This meeting is being recorded.
In this next section, 11.5, we're going to begin to look at what's referred to as retrosynthetic analysis. So, simply put, or in simple terms, this means that we're going to work backwards. We're going to look at our product and try to figure out what step before that we can create that product from what starting material. So we'll take a look at some specific examples, but we're still going to need to answer those same two questions. So we're going to have to see if there's a change in our carbon skeleton, or if there's a change or in the functional group or position of that functional group. So we're still going to look at these same two steps, whether we go forward or in retrosynthetic analysis. So as part of step 1, we're going to analyze the structure of the reactant and product and take a look at what functional groups we are dealing with. So let's take a look here. This is our starting material, this alcohol over here, and our product is now an alkyne. So has there been a change in the carbon skeleton? No, we still have the same amount of carbons, but there has been a change in our functional group. So sometimes you'll see both. In addition of carbon skeleton and change of functional group or relocation of functional group. Sometimes you'll only see one. So let's focus on the last step here. We need to think about what types of reactions can be used to make an alkyne. So we're going to focus from that last step first. So we've seen that things such as vicinal dihalides, so whether we have a vicinal dihalide here or geminal dihalides, we could we could create an alkyne. So elimination of any of these three dibromides, but the vicinal dihalide is the only one that we know how to make so far. We don't know how to make a geminal dihalide, so that's what this little caveat is mentioned here. So let's keep moving, and now that we've selected a vicinal dibromide, we're saying to ourselves that this alkyne, our product, can be made from this dibromide. And what reagents do we use? Well, we do two eliminations, right? So we have this dibrominated alkane. We do two eliminations using excess sodium amide and then water to protonate, right? Our alkyne product. So let's keep working backwards and see what other steps we have to consider here. So how could we make that vicinal dibromide? So we saw in our chapter of addition to alkenes that we could create a vicinal dibromide with this type of alkene here. So we could use Br2 in this reaction to form that dihalide. So now we have multiple steps. So we've seen the dihalide can be used to create our alkyne, and we can start with an alkene, and using Br2 and carbon tetrachloride, we can create this vicinal dihalide. So now we need to bridge the gap between our alcohol and our alkene. How could we create an alkene from an alcohol? So we could be thinking that we could convert this alcohol to a tosylate and then use a non-nucleophilic base, so we don't have a substitution. So this prevents substitution reactions, right? So no substitutions. We would only have an elimination then, right? So we would have an elimination that results using this DBU or DBN instead of a nucleophilic substitution. So that's how we can use tosyl chloride and pyridine to create this better leaving group, the tosylate leaving group, and then perform an elimination to end up with our alkene. So throughout this retrosynthetic analysis, you saw that we worked step by step backwards. So our first backward step, we saw that we could have a dihalide and then perform 2 eliminations. So that's what these steps here in 4 and 5 indicate. So our dihalide to our alkyne, and then we had, how do we create that dihalide from an alkene? We use Br2 and carbon tetrachloride. And then our first step to create, our first step, we had 2 steps in. We had that tosyl chloride and pyridine to change our leaving group, and then our elimination to go from alcohol to alkene. So we should make sure that when we work these through forward direction now, we could make sure that the regiochemistry and stereoselectivity are correct if we do have any stereoisomers created. And we should always remember that when asked to perform an efficient synthesis, we always want to have our desired product be our major product. So we should not create any major product. So we should not create any minor products through our selection of the reagents chosen. So we will continue with our last section in chapter 11 next time. And of course, we'll work through some more practice problems from this section from problems in the textbook.